Good evening, everyone. In this opportunity, we're from Group 6 are going to present about our solution to case 6. So this is our group member.
My name is Kia Sabian.
My name is Arunika Sadeva.
My name is Amin Fahri Arif.
My name is Henry D. Nathaniel.
My name is Arya Putra Tayla. Starting for the decomposition, the main problem is it is to form several strong and complementary student teams to complete a project. So we have to choose suitable students based on the data of personality types, their preference, activities and involvement, technical and non-technical skills, and each student's personal motivation and goals. For some problems, we have to consider what important information is relevant to this problem, which is the GPA of the students. And then moving on to the pattern recognition. So for GPS distribution and balancing follows a pattern that starts by sorting students in descending order based on their GPA, ensuring that the highest GPA is assigned first. Each student is allocated to the group whose GPA is closest to the target average, with the group's GPA being updated after every assignment. For balancing, the deviation of each group GPA from the target is checked, and if the difference is significant, students are swapped between groups to reduce the deviation. The swapping process continues relatively until the GPA differences across all groups are minimized, creating an optimized and balanced distribution of students.
Moving on to abstraction. So the process can be simplified into a general process. First, sort students by the average of GPA, then divide these items into groups. Make sure to keep each groups as close as possible to the average GPA. After that, you check if any group is too far from the target, and if needed, and swap items between groups to make them more equal. This continues until all groups are balanced as possible. For the algorithm, create workflows for each team to ensure step-by-step progress towards the final goal. Assign tasks based on the student's learning preference and personality types to maximize efficiency.
Okay, for the studio code of this problem, first we need to make some initialization. We set X as the total number of students, Y as the desired group size, in this case, maximum of 5 students, which means Y is less or equals than 5. Z as the GPA average of the class, and then after that, we create an empty list of groups. And then we go to the group formation. While X is more than 0, if X is more or equal than Y, we need to create a group of Y students, add the group to the group list, and subtract Y from X. We keep doing this up until if X is more or equal than 3 and less than Y, we create a group with the remaining X students and add this group to the list, and then set X to 0. Else, if X is less than 3, distribute the remaining students evenly across the existing groups and set X as 0. And then we move on to the GPA distribution for each group. Sort all students by GPA in descending order, and for each student, starting with the highest GPA, we assign the student to the group whose GPA is closest to Z value and update the group's GPA after each assignment. After that, we need to do some GPA balancing. For each group, if the group's GPA deviates significantly from Z, we need to find students in other group who can be swapped to balance the GPA and swap students to get the group's GPA closer to Z. Continue this process until the GPA deviation is minimized. For output, we will get a list of groups with students with a balanced GPA average.
Next, we move to the flowchart. So first, we start by set Y as the desired group with max 5% and X as the number of student. And after that, we can create an empty list and create group of Y student. If the remaining X less than 3, then distribute X to the existing Y. And if the remaining x more than 3, then create new group with the member of x, and we obtain the group. At the same time, we start by set zx GPA average of the class, and then we sort the students by GPA, and we assign each student to the group with the GPA closest to z. Next. And then after we update the group GPA, if the group GPA deviates significantly from the z, then we swap the students to balance the group GPA, and we go back to the update the group's GPA. But if the group's GPA doesn't deviate from z, then we obtain the group list and end the flowchart. Next.
Next, we find the big O notation of the pseudocode and flowchart that we've made before. Now, the big O notation is a notation that explains how an algorithm responds or grows responding to the input, how if the input is increased or decreased, or if the input grows. Now, to be able to understand the big O notation of our pseudocode, it is best that we divide the pseudocode into parts or divisions first, as each step has its own different big O notation. And we divide it mainly by initialization, group forming, GPA assigning, and also GPA distribution. Now, first we move on to the initialization. Now, in initialization, first of all, we set the parameters basically for our pseudocode, which is set x, set y, set z, and creating an empty list of groups. Now, the time or the space needed for this part of the algorithm doesn't grow or respond significantly to the input, if our input grows. So we can say that for this part of the pseudocode, the time it takes is constant. Therefore, we can also say that the big O notation for this process is O1. Next, we have group forming. Now, the big O notation of this part, we can analyze it by taking the time it takes for this process. So we can see that this process heavily relies on the number of x, which is students, which is being divided by the number of y, which is students per group. So the big O notation for this process is actually OX divided by y. But if we take y as a constant, as we've said before at the beginning, we can say that the big O notation of this part of the process is OX. So it really just depends on the amount of students. Next. And then we have GPA distribution. Now, we can see that the process of GPA distribution is a sorting process. Now, a sorting process is a log linear process. So we can say that the big O notation of this is OX log X. So it's the amount of students times the log base of the amount of students. Now, we then assign the group that is closest to each, we assign the students to the group that is closest to each group. So here we introduce a new variable, which is G. Now, G is the amount of groups that has been formed, and G can also be written as X divided by Y. Now, since we need to take into account the amount of students and group, the big O notation is now also OX times G. Now, OX times G can also be rewritten as OX to the power of 2 divided by Y. And as we have said before, Y is a constant. We can also say that the big O notation of this is OX to the power of 2. So actually, the big O notation for this GPA distribution is OX times G and OX log X. And then now for GPA balancing. Now, similar to the last part, GPA balancing heavily relies on the amount of students and the amount of groups, as we need to check we need to check for the individual students, and we also need to check in each group to be able to balance it correctly. So the big O notation of this would be G, the amount of students, the amount of groups, sorry, times by X, the amount of students, which can be simplified, as we mentioned before, to OX to the power of 2. So in conclusion, each step has its own different big O notation. For initialization, it's O1 because the time that it takes is always constant and never changes, depending on the input. And then group forming, which is OX because it depends on the amount of students. GPA distribution is OX to the power of 2 and OX log X, but here we're only taking the most complicated big O notation, which is OX to the power of 2. And then for GPA balancing is also OX to the power of 2 because it depends on the amount of students and the amount of groups. And to be able to take the big O notation of our pseudocode, we take the most sophisticated or the most complicated big O notation. So in this case, the time complexity or the big O notation of our algorithm is OX to the power of 2.
That's all from our presentation. Thank you for listening.